Have you ever played with a rectangular wire loop near a magnet and noticed it tries to rotate? That's not magic, it's physics. When a current-carrying loop is placed in a magnetic field, something fascinating happens. Due to the interaction between the current and magnetic field, the loop experiences a torque, much like how a door rotates on its hinges when you push it. The opposing sides of the loop feel forces in opposite directions, causing a twist. This rotational effect is captured beautifully by the formula tau equals n times I times A times B times sine theta, where tau is torque, n is the number of turns, I is current, A is area, B is the magnetic field, and theta is the angle between area vector and magnetic field. As you can see in the diagram, the sides of the loop feel opposing forces, leading to rotation. Now let's dig into how direction plays a role. The area vector A is perpendicular to the plane of the loop, and we use the right-hand rule to find its direction. Curl your fingers along the direction of current. Your thumb now points in the direction of the area vector. The torque vector, tau, is perpendicular to both A and B and follows the vector cross-product rule. Here's the key idea. Torque is maximum when the loop is parallel to the field lines, that is when theta is 90 degrees. It becomes zero when the loop is aligned with the field. This rotational tendency of the loop in magnetic fields forms the core working principle of electric motors. Let's now introduce a powerful new concept, the magnetic dipole moment. A current loop behaves like a tiny magnet. And just like a bar magnet has a magnetic moment, so does our loop. We define it as m equals I times A, where I is the current and A is the area vector. The direction? Again, right-hand rule. The stronger the current and the larger the loop, the greater the magnetic moment. Its unit is ampere meter squared. For instance, a loop of 2 cm radius carrying 5 amperes would have a magnetic moment of roughly 6.28 milliampere meter squared. This magnetic moment tries to align with the external magnetic field, just like a compass needle with Earth's field. Let's bring magnetic moment into the torque formula. Instead of tau equals Ni AB sin theta, we can now write tau equals m cross B. Yes, torque is the vector cross product of magnetic moment and magnetic field. The magnitude of torque becomes mb sin theta. So, the torque is maximum when m is perpendicular to B and 0 when aligned. The magnetic field tries to rotate the dipole so that m aligns with B, a behavior that's extremely useful in devices like galvanometers. Take a look at the diagram. The torque is perpendicular to both m and B, just as vector math predicts. Here's a beautiful analogy. Think of an electric dipole placed in an electric field. It experiences a torque given by P cross E, where P is electric dipole moment and E is the electric field. The behavior is identical to a magnetic dipole M in a magnetic field B. In both cases, the field tries to rotate the dipole to align it. The potential energy for magnetic dipoles is given by U equals minus m dot B. It's minimum when M and B are parallel. This deep analogy helps explain everything from how atoms align in magnetic materials to how compasses work. Let's solve a real example. A rectangular loop measuring 5 cm by 10 cm carries a current of 2 amperes. It's placed in a magnetic field of 0.4 Tesla at an angle of 30 degrees. First, compute area. A equals 0.05 times 0.1, that's 0.005 square meters. Next, the magnetic moment m equals I times A, which gives 2 times 0.005, that's 0.01 ampere meter squared. Now torque tau equals mb sin theta, or 0.01 times 0.4 times sine 30 degrees. That's 0.01 times 0.4 times 0.5, which equals 0.002 Newton meter. That's the torque acting on the loop. So to wrap up, a current loop placed in a magnetic field behaves like a magnetic dipole. It experiences a torque that depends on its magnetic moment and orientation with the field. The formula tau equals m cross b gives us both the direction and magnitude of this torque. We saw how this concept mirrors the behavior of electric dipoles and plays a crucial role in technologies like motors, galvanometers, and magnetic sensors. I hope you now understand how current loops mimic tiny magnets, and how torque drives the magic in rotating machines and measuring devices. See you in the next session with another exciting concept in physics.